Coming to system earthing, in case of three-phase supply, this is system neutral in three-phase supply. It is not connected to ground, so it is known as pre-neutral. This is three-phase system, whether it can be generator or secondary of transformer. These are the capacitors. These capacitors form between line conductor and ground. CR, CY and CB. These are the currents IR, IY and IB flowing through the capacitors. We are assuming that this is completely a balanced system, and line to ground capacitors all are equal value. Similarly, line to line capacitors, these are also equal in value. These are line to line capacitors. Coming to line inductance, the line inductance is also equal. That means line is regularly transposed in order to maintain equal impedance at regular intervals. The system is completely balanced and there are no faults in the system, and load is also not connected. These are the phase voltages and these are the line charging currents. Because of the capacitor, the currents are leading the voltages exactly by 90 degree. The system is completely balanced. The currents are completely all are equal in value. The phase voltages are also same. The value of current IR, IY, IB all are same. The value of current equals to phase voltage by XC. XC is equals to capacitive impedance equal to 1 by 2 pi FC. This is currents going through the capacitor. Here we are taking a equivalent circuit. This is source. This is three-phase supply. Going to load. Here load is not connected, so switch is in open condition. The neutral return current, neutral is not connected to ground. The neutral current IN is equals to 0 even though switch is open, even though switch is closed, because the start point of the system is not connected to the ground. And the other the case, when the load is connected to the source, the neutral current has to be vector sum of these three currents. But the start point of the system is not connected to the ground. Under balanced condition, IR, IY, IB, all these three currents will be exactly 120 degrees apart. So this is about three-phase system neutral grounding, when the neutral is not connected to the ground, but the system is completely balanced and there is no load and there is no fault. Even though if you add load to the source, the system completely works fine. But the system has to be completely balanced and there should not be any faults. In that case, system works. The two cases, we had discussed the two cases. One is when there is no load, on load. In both the cases, system completely works fine. But the problem occurs only when fault occurs. We are assuming a fault in B phase. At the fault location, the voltage will be 0 and it draws currents from all the directions. Here we are assuming that load is not connected, so it draws current only from the source. This is the current path. IR and IY, these are traveling respective phase windings and traveling back to the B phase. IC is the fault current or charging current, which is sum of IR and IY. This is vector sum. The phase angle between IR and IY is 60 degree. IC equals to whole under root IR square, IY square, 2 IR, IY and cos 60. IR and IY both are equal in value. So we are considering this one as a value. So a square plus 2a square into half. So finally it becomes charging current equals to under root 3a square. So charging current equals to root 3 into IR. Take the IR and the line voltage VBR is perfectly leads by 90 degree. The IR current leads the line voltage VBR by 90 degree. Similarly, IY leads the VBY by 90 degree. So here we are considering the line to line voltage. The line to line voltage equals to, here this part will be line to line voltage. Line to line voltage VL equals to root 3 into V phase. So finally root 3 becomes 3. So this part, the charging current IC equals to 3 into V phase by XC. So during fault condition, when the system neutral is not connected to ground, the charging current is 3 times of the first case. Again here we are considering equivalent circuit. This is source. The system neutral is not connected to ground. Here is 3-phase supply. One of the phase is connected to ground or faulted and load is not connected. Return current IN, the current which is flowing into the neutral of the system, that is 0. Even though switch is closed, even though switch is open. And at the same time fault is present in the system, the total system is imbalance. And the neutral current is not equals to vector sum of IR, IY and IB. Coming to main important topic, arcing. What is arcing? As there is short circuit from line B to ground and this charging current IC flows from line B to ground. If this current is sufficient, if it ionizes the area present between the conductor B and ground, then arc will form and the arc is being maintained by this fault current. As long as the fault current is present in the system, the arc will be present. So these are the effects of not providing system neutral grounding. So in order to minimize this arcing effect, we are going for system neutral earthing. Coming to solidly grounded earthing system, here the neutral of the system is connected to ground and a fault occurred in line B. So the voltage at fault location is 0 and the fault current is being fed by charging currents IR and IY and the fault current IF. This is the direction of IF, IR and IY. At this node, if we apply Kirchhoff's current law, the IF equals to IC. IC equals to vector sum of IR and IY. If the system is balanced or unbalanced, if the fault occurs in the system, the fault current is being fed by other phases and the fault current. Lines are regularly transposed to maintain equal values of inductance per line. Here the neutral is connected to ground, so the return current is vector sum of IR, IY and IB. When system is balanced and there is no fault in the system, then the return current is 0. If there is unbalance in the system, then the return current is not equals to 0. During faults, the arcing effect can be minimized because the system is solidly earthed. The total fault current either may be from 0 to infinity. This fault current can be diverted to ground, or this fault section can be isolated from the healthy section with the help of protective devices. Coming to NGR, neutral grounding resistor. So the resistance can be varied from 0 to infinity. Ideal condition, if it is 0, then it is equal to solidly grounded system. If it is infinite, that means it is open circuit. The neutral is equal to free neutral. The fault current, same as the previous case, fault current, and this is charging current. Charging current is sum of the IR and IY. For example, from 0 to X, the fault current is being limited by the resistor NGR, and the fault currents access to this value X to infinite, and the fault sections are isolated by the protective devices. Coming to a very important topic, arc suspension coil or Peterson coil. In this case, the fault current and the charging current both are exactly 180 degree phase opposition. This current is passing through the inductive coil which lags exactly 90 degree. These currents are passing through the capacitor, which leads the voltages by 90 degree. The IC and IL both are 180 degree phase opposition. If the current, charging current and inductor current, when these currents are both are equal in value and both are in phase opposition, then the arc is neutralized. the charging current IC equals to 3V phase by XC. The inductive current IL equals to V phase by XL. We get this equation. From this equation, we get this result. From this result, our final result is this. These two results are very, very important. So with the help of these formulas, the inductive value of the coil, the maximum current, fault current carrying capacity of the inductive coil, what is the maximum kVA rating of the coil. Such type of numericals we have to solve.